This video will continue our discussions of planes in 3 space by answering how to find the distance between a point and a plane. So we have a plane P there in orange and a point P there in red off the plane. I went ahead and drew a normal and gave my normal components because we're going to use that. Now, I want to think about this. Let's create a point down here. We're going to call this random point on the line. We'll call it x naught, y naught, z naught. Right? We'll call it p naught, the point. All right. The distance between this point and that plane is not the distance. Remember, I'm going to go and draw it because we're going to use it. It is not just the random distance from any point on the plane to the point. The actual distance, by definition of distance from a point to a plane, is the orthogonal distance. So it's like the straight distance straight down. It's kind of hard to see from here because we don't know where the point's going, but let's say it's like right here, and that's where it went. It makes it an orthogonal. That is the distance that we're looking for. Now, imagine if you think about that, we have that distance. We actually can create a triangle here over to my projection to draw this like right angle, and this distance from this point to down here, this distance is called d. Let's call it that. It's not the magnitude of n. It could be any distance. I don't know. I'm just calling the distance from this point to that point. That is the distance between the point and the plane. If we think about it there, that's my my vertical distance as an orthogonal. That would be the actual distance between the point and the plane. You could put that p naught anywhere on the plane as long as p stays still, and that vertical distance is going to stay the same. Now, this distance will change, and this distance will change, but that vertical distance will not change. It will always stay the same. Think about moving p naught all the way around anywhere on that plane and leaving p where it is. That distance stays the same. So what we're going to do is use the idea of trying to take this vector and capturing this one. I want to create that to be a vector. Well, that looks like a projection, right? Remember, this is if I had a sun here and the sun was shining, the sun shines right onto that vector, giving me that. That was called a projection. So let's write that here. The distance d is going to be not the projection itself. The projection itself is a magnitude. The projection is a vector. We want the magnitude. So we're looking for the projection of the vector p naught p onto n. Right? There was a name for this too. This was the component projection, and we wrote it like this. Either one will work for me as long as you know what you're looking for. We're not even going to use, we'd have to figure out what that definition is and work backwards and do all that. We're going to come up with the formula pretty quick. We have that. That is my distance. The equation for that, and we're not going to derive it again, was the dot product between my vectors, the actual vector going to the point and the normal, and we want the absolute value because it's going to be distance, and then we're going to divide that by the magnitude. That was using the definition of component. If you look up the definition of component, that is the formula given. All right, well, we can work backwards with this. P naught P is actually that vector. If we were to define it, we go to P minus P naught. I got X minus X naught, Y minus Y naught, and Z minus Z naught. And then I have vector N, which is up there, ABC. So if I dot those, okay, the distance between a point and a plane is equal to the absolute value of A times X minus X naught plus B times, that should look familiar, Y minus Y naught plus C times Z minus Z naught. That absolute value divided by the magnitude, and I'm going to just write out the magnitude definition. Magnitude definition is a squared plus b squared plus c squared, the square root of all of that. So that is the definition for distance. We can actually even take it a step further, notice up top is the equation of the plane, while the bottom is just the magnitude of your normal vector. So notice in a problem like this, if they asked me to give the equation of the plane, or sorry, the distance between a plane and a point, I would just use the plane on top and I would plug the point in question on top, right? And then on the bottom, I just find the magnitude of that. We could also write this as the same thing on the bottom. Man, my handwriting today. A squared plus B squared. You're like, it's not any different than normal. Sorry, guys. I try my best. All right, we got AX plus BY plus CZ minus D. I could use that formula as well. Either one of those will work for the distance between. So we just use that formula. This one's pretty straightforward. We actually don't use it that much, but it is a nifty way to use the normal to come up with this formula.